Okay, so let's get started. Today we were talking about the combustion of homogeneous propellants. What we are sort of going to do is do a little analysis that describes that we can use to estimate the burning rate. This is more of a phenomenological analysis. It will not give you quantitatively correct numbers, but it will get the scaling effect right. And what we are going to show with the analysis is that we can use a basic analysis and show that RB, or the burning rate of the propellant, is equal to some coefficient times pressure raised to some exponent. Okay, and then we're going to make a lot of simplifying assumptions to do that. But in how a real homogeneous propellant burns, is that you can divide the burning of the propellant into at least 5 different regions. We have a condensed phase preheat zone, and all that is happening in the preheat zone is there are no reactions. We just have heat conduction from a higher temperature region propagating and heating up the cold reactants. And so there's a slight increase in temperature. Then not quite at the surface, but just below it, there's a really complex condensed phase reaction zone. This can be a melt layer for some propellants. There can be bubbles forming in here, or it can just be a condensed phase reaction zone where you have basically a solid material of an alpha crystal phase sort of reacting and turning into a beta crystal phase. And even at some pressures, this melt layer, if there's a melt layer that forms, at some pressures, the melt layer can even be supercritical. And so this stuff gets complicated really fast. And then above the surface, there are pyrolyzing gas phase species. These species are like nitrogen dioxide, HONO, like in a soup of methyl radicals, HCO, CO, CHOCHO, H, etc. And so these species are really reactive. And so when they get the chance, they actually chemically react fairly quickly in a zone called the fizz zone. Again, don't ask me why it's called the fizz zone. Then the products of the fizz zone species are fairly stable at lower pressures, and they take a while to react. Then after an ignition delay period, in this region in the dark zone were the sort of intermediate species. After the combustion of the fizz zone layer, there's an ignition delay, and then those species chemically react to form the luminous zone of the flame, which you clearly see right there, and basically raise the temperature to the final adiabatic flame temperature for the propellant. Okay, and so I got the basic zones listed here. And so those are listed right there. And I just discussed those. And so now we're going to perform a phenomenological analysis. And just to understand that we can't use the simplified relationships that we use for detonations, is let's just look at the Rankine-Hugoniot diagram on the PV plane for a deflagration. So here we have the unburned Hugoniot, and here we have the equilibrium Hugoniot. And here we have the Rayleigh line for a CJ flame. Most flames don't live there. You guys have a homework problem on a CJ flame propagating in a closed-end tube for a gas mixture. When we discuss the initiation of detonations, you'll understand that that's a very unstable configuration, mainly because it's not just a nice flame, but you have a flame right here, and there's a precursor shock in front of it. And the Mach number of this precursor shock can be on the order of 2.5 to 3. And the shock will be moving faster than the flame, so there's more distance between here and here. So you have these high temperature shock heated gases that can ignite and burn on their own if there's enough distance between the shock and the flame. And so actually CJ flames for that reason are very unstable. Or if you have a tube or you have a realistic scenario and say there's some rubble here, like a big rock or something, the shock can actually impact this and reflect backwards. And in the reflected shock region, you will substantially raise the temperature, and you can actually induce auto ignition via a Semenov type criterion of the gas here before the flame before the flame gets to there. And so for reasons like that, these Chapman-Jiguet flames are very unstable. They don't live very long. And in reality, the closer and closer you get to the CJ flame condition, the more and more unstable your flame becomes. Now, where most stable flames live is basically very close to the very top of the lower of the deflagration branch on the Hugoniot. And because most flames live here, we don't have the tangency condition to basically find them. It's now what's called an eigenvalue problem, meaning that to know the correct flame speed, you also need to know the structure of the flame. And so how fast these flames go or how fast the propellants deflagrate or burn is dependent on the structure of the flame, how fast the chemical reactions occur, thermal conductivity, all of that stuff. So whereas for a planar detonation, we just needed to know what was basically what was going in the control volume and what was going out of the control volume. If we drew a control volume around the entire detonation. For a flame, it does not work like that. That doesn't give you all the information that you need. You need to know what's going on inside of that control volume. Okay, so I already discussed that. And so here we're going to do a simplified analysis. We're going to assume a steady flame propagation or a steady burning rate. We're going to assume constant pressure conditions. We're going to assume that the flow is perfectly 1D, that there is no cross flow. We're going to neglect the dark zone. We're going to assume constant properties. You're going to assume negligible mass diffusion. And in fact, for our assumption of constant heat or constant properties, including specific heat, this is actually not an assumption, it's exact. And we'll assume no reaction in the condensed phase region itself. We will assume that all of the condensed phase reactions occurs immediately on the surface of the propellant. Okay, and also we are going to perform our analysis in the stationary frame of reference. So that is, in a real experiment, you have a strand of propellant that ignites and then burns downwards. And so the surface here is moving. We have some sort of a flame which may be conical just due to real geometrical effects. And the surface may be may not be perfectly flat and stuff like that. And for this analysis, we can't possibly account for all that stuff. And so what we're going to do to simplify it, basically, rather than having a stationary strand and the surface burning downwards, we're going to assume that the surface is stationary, and we're going to be feeding the strand from the bottom at some velocity RB, and that corresponds to the burning rate of the propellant. Basically, because the surface is trying to burn downwards at velocity RB, so if we keep feeding the solid material up at velocity RB, basically the upward feeding velocity of the propellant and the downward burning rate basically exactly cancel out, and the surface is stationary. Okay, and so we will assume that the flow then is also perfectly 1D. So rather than having the actual sort of traditional flame structure, we're just assuming that everything is perfectly 1D. Okay, that there's no spatial variation in the tangential direction to the surface. Okay, and then we're going to define X to be attached to the surface and pointing into the gas phase. Okay, so are there any questions with this so far? Okay, so now we're going to split the domain into 3 control volumes to do this, because essentially we want to determine how fast, we basically want to find how fast we need to feed the propellant in to produce an equilibrium flame structure, and we don't know that value. And so that's why this is called an eigenvalue problem, is that you don't know how fast to feed in the reactants to produce a stationary flame. Okay, and so for gas phase flames, that's called the laminar flame speed problem, and and you determine a quantity called S sub L, which is the laminar flame speed, and RB for a propellant is the exact same thing. It's just that it's a bit more complicated because you have this condensed phase material and all of those different zones that I talked about earlier. For gas phase flames, you arguably have either 2 or 3 zones, depending on how you split them up. But for condensed phase combustion or propellants, you have at least 5. So now, how we're going to go about doing this, the strategy of how we do this is we need to basically split our integration into 3 different control volumes, and then basically match the heat flux or do an energy balance at the boundary of all 3 different control volumes. So the first control volume will be just in the condensed phase region itself. The second control volume will be an interfacial control volume. Yes, those evil, nasty things that I discussed earlier in class, we're actually going to use them. And then the third control volume will be in the gas phase region itself. So we basically split the domain into 3 different regions. And then basically what we are going to look for then is basically we are going to match the heat balance at the surface of the propellant, such that the heat conduction that the heat flux from conduction going into the solid propellant is equal to the heat flux going in to the top of the surface from the gas. Basically, if that energy balance is met, we have achieved in finding our equilibrium flame structure. And if our burning rate is incorrect, then basically that heat flux balance will basically not be met, and you got to guess again. But for the assumptions that basically we are going to make, you can actually solve for RB. But in your computer project, that's essentially what you need to do, or what your code will do, is it will integrate the structure on the gas phase side. Then you can find the heat flux, and then check the balance, and then check an overall energy balance, and make sure that the heat going into the condensed phase propellant basically matches, is basically balanced with the rate of energy that you are feeding into the propellant by just basically moving it up at velocity RB. And if they're matched, good, you know your burning rate and the flame structure. If they're not, you need to guess again with RB and with a new burning rate and repeat again. Okay. But for this problem, we don't need to do that. We can solve it analytically. So now we're going to work with the condensed phase region. And so here I'm just drawing a giant control volume around the entirety of the condensed phase region. And that includes the preheat zone and the condensed phase reaction zone, which of course we are completely neglecting in this analysis, but I just drew it here anyways. Okay, and so we have heat flux going in from the left. We have the flow of enthalpy going in from the right. That's just CP. That's just basically we are assuming constant specific heat, so that's just CP T naught. And we have a heat flux going out from the top. This is still in the condensed phase side, so this would be x equals 0 minus. So this is still barely inside of the condensed phase material. Okay, and then we have a flow of enthalpy going out, and that's it. Now I like to draw my heat fluxes going in the positive direction. So if we need to pop them into the differential equation, you do that I don't make silly sign errors. And then also we will assume that the surface temperature of the propellant is at some temperature Ts, and we don't know what that is. And that's another little point that we need to find. Okay. Okay. And then our control volume will extend all the way from x equals minus infinity. So we have an infinitely long piece of propellant that we're basically feeding in, that we're basically feeding in, and it's going to stop, as I said before, just it's still in the condensed phase of material side of the interfacial energy. Or it's basically just it's basically at the surface, but just a little bit in the condensed phase side. Okay. So now we're just going to do conservation of energy. And I'll just do this the way you did it in heat transfer in the most simplistic form possible. No need for super formal RTTs here. Okay, and so we'll assume you can cross out the unsteady term because we're assuming it's steady or quasi-steady. We are neglecting internal energy generation due to condensed phase reactions. Okay, and so we only have energy going in and out through the surfaces of our control volume. So we basically do that energy balance. And we argue, and so now we do that energy balance, and we argue that this point here is at x equals minus infinity. What do you think the temperature gradient will be at x equals minus infinity? Far, far, far away from the surface.
0.
Yep, it has to be 0. If it's anything other than 0, the condensed phase propellant temperature will either be minus infinity or plus infinity at x equals minus infinity. Okay, so it must be 0. So when we do the energy balance, this term here goes to 0 because basically the temperature gradient must be 0 at minus infinity. And then we are just left with basically these terms here. So we are feeding it in at velocity RB. So this is just the enthalpy going into the control volume. This is the heat conduction. It's going in from the top, and this is the enthalpy leaving the control volume. And so we just solve for basically solve for the heat conduction flux, or actually the negative of that, in terms of the surface temperature and the initial temperature of the propellant. Okay, and so that's just a fairly straightforward energy balance analysis. Now, to complete the analysis of the burning rate, you don't need to determine the condensed phase temperature profile because we already have our condition. Because we already know we already have our condition in terms of thermophysical properties, with the exception of the surface temperature of the propellant. But I'm going to integrate the condensed phase temperature profile, and then because you can learn a lot from that for a burning propellant, and that will have consequences for rapid transient events. Okay, so and you can show that the governing equation for the temperature of a propellant, if it's steady, is this equation here. And later on in the lecture today, I'm going to derive this for a gas, for the gas phase region. And then essentially, if you apply the boundary conditions, that T at minus infinity is T naught, and T at 0 is equal to some surface temperature, and you can integrate this. You can show that if you have constant properties and no internal heat generation due to chemical reactions, you can show that the temperature profile looks something like, basically has this functional form here. It's the initial temperature plus the difference in temperature between the surface and the initial temperature of the propellant times E to the burning rate times X over alpha P. And no, there's no negative sign here because our X goes from minus infinity to 0. Okay, so basically this exponential term goes between 0 and 1. So the reason that this structure is important is it tells you a lot about how the energy is stored inside of the condensed phase propellant uh, at different burning rates. Okay, so let's just qualitatively look at a few profiles in the condensed phase. So this solution here has a shape that will look something like this. It'll start out at TS, and then it will exponentially decay and then basically asymptote to a temperature T naught. And as you increase the burning rate, this curve becomes sharper and sharper and then basically sharper. Okay, and so you can then now that we sort of have an idea of what the temperature profile is, you can actually compute the amount of thermal energy that is being stored inside of the condensed phase propellant by basically integrating under this temperature curve here. Okay, and so basically this area here, if you were to integrate it, would basically be it would be representative of the amount of energy that is stored inside of the propellant. And notice that this curve here is much more broad for a slow burning for a propellant that's burning at a slow rate versus a propellant that is burning at a fast rate. Okay, so what this means is that more energy is stored in the condensed phase when the burning rate is smaller. Okay, and then note that RB equals AP to the N. So then the fact that if we are burning our propellant at a low pressure, we can have this much stored energy in the propellant over here. But now say we suddenly bump up the pressure of our system, and the equilibrium amount of and the equilibrium energy stored would just be this tiny little region here. So we've now stored less energy, but we've suddenly bumped up the pressure. So basically, the profile will meet this new equilibrium state, but in this region here, we have all this extra stored energy inside of our condensed phase propellant. Okay, so that's basically extra energy. And basically we will discuss that later, but that extra stored energy has consequences if you rapidly change the pressure condition in your basically in your rocket, is that it can produce combustion instabilities. And the exact opposite thing occurs, that if I'm burning at a very high pressure and I suddenly decrease the pressure, is that to stably burn the propellant, I need this amount of stored energy inside of the propellant. But if I suddenly decrease the pressure, the amount of stored energy is only in this tiny little region here. And so I don't have enough energy to basically burn the to basically stably burn the propellant, and that also has that also has consequences if I rapidly decrease the pressure. If I decrease it enough, you can even quench the propellant. In fact, that's one of the only ways that I know of to quench a propellant, is to rapidly depressurize it. So if in the days of the solid rocket boosters, if something went awry, you basically had to blow up the solid rocket boosters to keep them from burning. And that's actually a little knob that the controls that the control people had, was to basically blow the thing up. Because if they went awry, it would be better to push the button rather than to have some crazy rocket booster flying into some city and damaging that. Okay, and we will discuss this concept more on transient a propellant, a combustion, at least qualitatively. But yeah, so just what we gleaned from just integrating this this temperature equation here you can already learn a lot about the burning of a propellant. And so, um, basically why this profile gets broader the slower the burning rate is, just has to do with heat conduction. Is that I'm not going to call it, well, it's called a is that basically this here is called a thermal wave. I hate the term thermal wave because it's not a wave equation that is causing this. But basically the thickness of this thermal wave is dictated by the amount of time that basically heat conduction has to basically heat up the material. Is that the rate of heat conduction is not dependent on the burning rate, but the faster you burn the material, the less and less time that heat conduction has to actually heat the condensed phase material. Okay, and then note that I drew these really fat, but at high pressures, at like normal mortar operating pressures for a rocket or a gun system or tactical missile, the thickness of the thermal wave can be on the order or less than even 1 micrometer at high pressures when the burning rate is high. So these structures here are extremely thin. Okay. And also, that also has a consequence for igniting a rocket, is that to stably ignite a rocket, you typically don't do that at low pressure. You need to do that at a raised pressure. And the reason that you don't do that at a low pressure is because to get it to ignite stably, you need to store all of this energy here inside of the propellant. Whereas if you say raise the pressure a bit and then try to ignite it, you only need to store this little bit of energy here. And so it becomes easier to ignite. And so just from looking at that temperature profile at different burning rates, you can actually glean a lot of really important physics about propellant combustion. Okay, so enough about that aside. So now we've basically worked on the condensed phase side. We have determined a relationship for the conduction heat flux on the condensed phase side of the interface in terms of the burning rate, the specific heat of the propellant, the density of the propellant, the surface temperature of the propellant, and our initial propellant temperature. Okay, so now we're going to do we're gonna work with an interfacial energy balance to relate the heat flux on the condensed phase side of the propellant surface to the gas phase side of the propellant surface. Okay, so now we'll apply the interfacial conditions, and so basically we have a stationary propellant surface. So that would mean that the normal velocity of the interface is 0. And so we can just draw a fairly normal looking control volume here, where we have our piece of propellant here. And then for conservation of mass, we can apply the conditions that I derived earlier for conservation of mass to show that basically rho g ug is equal to basically rho p rb. Basically that the mass flux is constant. Okay, but due to the massive density difference between the gas phase and the propellant, you will have a very large change in the density. So even if the propellant is burning at, say, 5 millimeters per second, the gas will be flowing on the order of, say, 10 centimeters per second. So there's a pretty big change in the gas phase velocity. Okay. Now we will apply energy balance. So here we just draw our same control volume right here, only this is at the interface here. So we have our condensed phase material entering the control volume at temperature Ts. We have the net enthalpy of the gas leaving at temperature Ts. Remember, this is exactly at the interface. So the gas phase temperature and the condensed phase temperature are both at the same temperature because it's physically the same point, but it's just that the condensed phase side is just little teeny is a teeny little bit inside of the condensed phase surface, and the gas phase side is just a teeny little bit on the gas phase side of the surface. We have the heat conduction fluxes, and then in general, you have intense radiation from the combustion products, or even an experiment, you may have a laser that is heating them up. You would need to account for that in a real case. And then also, we can have some reactions occurring on the surface. And so for our energy balance here, that would look like an internal heat generation term that is occurring inside of our control volume. Okay. Okay.
So do we need to, are we not concerned with energy due to phase change from condensed phase to gas phase?
That would be taken up in, that would be taken up.
Okay.
That would be taken up in the enthalpy.
Gotcha. Okay.
Yeah, and you could sort of think of that as a heat of reaction. And so you could think of a condensed phase reaction or a surface reaction could be evaporation. Is that we're essentially treating phase change like a condensed phase reaction. And so if it was a purely vaporizing propellant, like say nitromethane, this heat of reaction would just be the latent heat of vaporization. But for a solid strand of propellant, like say JA2, which is a double base propellant, then it would be the heat of reaction of the net pyrolysis species. You know, the heat of reaction that basically converts the condensed phase species into pyrolysis species. Okay. So then we do the energy balance, and then you can apply these same conditions that I derived in class. And so there's nothing new here. We are neglecting the effect of any shear stress. And we're going to, there's no radiation inside of the condensed phase. Okay, so we're assuming that the condensed phase is very optically thick, meaning that thermal radiation cannot penetrate inside of the propellant, which may or may not be a good assumption. But we're going to assume it anyways. And also, even if it's a liquid, we are going to be neglecting any of the surface tension effect. So here's the surface tension, just due to the normal surface tension effect, or no, this here it would be a sort of work due to the Marangoni stress, and this here is work due to a normal surface tension, just due to just normal surface tension effects. Okay, so if we were to define, if we were to start with the enthalpy and then convert the enthalpy into sensible enthalpy and a chemical energy term here, and you work with this equation here, what you wind up with is this expression right here for the surface energy balance. And again, this can be obtained either by working with this more general expression that I derived in class, or just a nice interfacial energy balance here, because it's just a normal control volume analysis. Just that your control volume is super thin, is basically the only difference. Okay, but anyways, so we have our overall energy balance. We have the difference in sensible enthalpy entering and leaving. The control volume, we have the difference in conduction heat flux entering and leaving the control volume. And we have basically a sort of surface reaction that is either vaporizing or pyrolyzing the propellant with a heat of reaction. If you were to include the chemical energy in the enthalpy, then you would not have this term right here. But for analysis, it's much easier to work with the equations in this form here. Okay. And then you can also apply conservation of mass. This is a bit like your one homework problem to show that the surface reaction rate is just equal to the burning mass flux rho P RB. That's similar to what you guys did for that one homework problem that I gave in homework set 3. Okay, and then plus any extra thermal radiation. And thermal radiation can be a pretty important component of propellant combustion, just because you saw from that burning propellant, you have all these really of that heterogeneous propellant. You saw all those really bright burning aluminum particles, and the flame temperature for those is about 4,000 Kelvin. So you have really super intense radiation from a cloud of burning particles, and that thermal energy impacting the surface and further heating it up. Okay. However, for analysis purposes, we're just going to pretend that that term does not exist. Okay. Then then we're going to pretend that that basically the thermal radiation term is small, and then we are also going to assume that I didn't write this. Assume that the specific heat of the propellant is approximately equal to the specific heat of the gas, because they typically are of the same order of magnitude. You know, they're not that different. And again, we are not after a quantitatively correct analysis. That does not exist. You can relax a lot of the assumptions that I'm making here, and you just get more nasty formulas that you still have to go to the experiments to calibrate them anyways. And so basically all we're after here is saying, basically, can we basically look into Saint Robert's law and glean some physics of and glean the fundamental physics of that coefficient and that exponent on the pressure. Okay, so if we assume that the specific heat of the gas and propellants are close, we can get rid of this term here. Then we basically simplify the surface energy balance at the interface, that the heat that the conduction heat flux on the gas phase side of the surface is equal to the conduction heat flux on the condensed phase side of the surface, plus the mass flux times the heat of reaction times the vaporization or net pyrolysis heat of reaction that is occurring on the surface. Okay, but we can go one step further here, is that from our condensed phase energy balance, we showed that this lambda, or that lambda p dt dx on the condensed phase side of the interface is equal to the propellant density times the propellant specific heat times the burning rate times the net temperature difference between the surface and the initial temperature of the propellant. So basically, we're going to use our result from the condensed phase energy balance, and we're going to plop it into here. Because again, because basically, if we just stopped here, we now have two unknowns. We don't know what this is, and we don't know what this is. And we're trying to relate these evil temperature gradients into basic properties of the propellant. Okay, so if you make that substitution and simplify, we now know that the conduction heat flux on the gas phase side of the interface is equal to this expression here. Okay, where it's basically equal to the burning mass flux times the net sensible enthalpy, a difference between the condensed phase temperature, or between the surface temperature and the initial temperature of the propellant, plus the heat of reaction at the surface. Okay, and so that could be, and that's usually endothermic, because it takes a lot of energy to sort of break apart and fragment a solid propellant into a bunch of little pieces. Or also if you need to vaporize it, that is also a very endothermic process. Okay, so now we've started at x equals minus infinity. We have worked in the condensed phase side of the propellant. Now and now we have jumped from the condensed phase side of the interface, and we have jumped across it, and now we are on the gas phase side of the interface. Now we got to work in our third region, and that's the gas phase side. Okay, and so after we find the gas phase side, we can find another relationship for the heat conduction flux on the gas phase side, and then solve for our unknown burning rate. Okay, and so for the gas phase side, that's actually a bit more complex. That's a bit more complex because of the chemical reactions that are occurring within the gas phase site. So we are going to simplify the analysis and make it doable, we're going to neglect the dark zone. Not all propellants have a dark zone, so it's not a horrible assumption. And also, you'll find at high pressure, the dark zone also disappears. So the dark zone isn't always present anyways. We're going to assume constant properties. That is the gas phase reactants that are exiting the surface of the propellant have the same specific heat as the final combustion products after the flame zone. Again, we're going to assume it's steady, and we're going to assume that the reactions are basically uniformly distributed in a reaction zone that starts at xi or at xi and ends at xf. Okay, and then basically we are breaking the gas phase region into essentially three different regions. Basically, this region here would be a region between the surface of the propellant and the start of the flame, or the start of the reaction zone. And basically, this would be a heat conduction zone where we're just basically heat conduction from the flame is actually making its way into the pyrolysis species and basically heating them up to the point to where they can rapidly burn. And then at the end of XF, there are no more chemical reactions because they are all spent. Okay, and so we're just looking after. Okay, so again, and then we're going to assume that the chemical reaction rate over here is identical to the chemical reaction rate over here. Okay, and so that's we're making a lot of lofty assumptions, and because of these are done to make it so we can actually integrate these. If you do realistic assumptions, like you are for your computer project, you have to go to the computer to solve these equations in the gas phase zone. There's no getting around that. Okay, and we're also going to make the really grand approximation that our chemical reaction is just R goes to P, and the enthalpy of the reactants is just some Cp times T, or I'll say CpG, Cp for the gas phase species, times a temperature, basically plus an enthalpy of formation for the reactants, and the enthalpy of the products is just Cp times T. Okay. So are there any questions with this so far?
I just have a question about, I guess, the initiation part of this. I know we're just kind of more talking about the steady state version now, but I was just kind of thinking conceptually, since you have to heat up those reactants by the flame, if you're just starting your flame, is the dark zone usually a little thicker as you start, and it kind of works its way back as the flame reaches its hotter steady state temperature, or is that
the dark zone tends to be, if it's a propellant that produces a dark zone, it tends to be very thick at low pressures, and it becomes thinner and thinner and thinner as you increase pressure. And that's just basically due to in the dark zone region, essentially you're just waiting for those species to start to react chemically. And the higher pressure is, the faster the rate of collisions between all those molecules is, and the faster the chemical reaction rate is. And so at high pressures, those reactions occur so fast that essentially the dark zone effectively disappears.
And then at the surface of the condensed phase, here, I thought we mentioned, or we're assuming that there are no reactions taking place in the condensed phase. Is that
Yep.
true? But in actuality, the reaction does start at the end of the condensed phase.
Yes.
Okay.
In reality, yes. In reality, it does. There's a little bit of reaction, and it's even complicated by the fact that you have that there can be some bubble formation, and you have reactions occurring inside of those bubbles. It gets really complicated.
Okay, thank you.
Yeah, and so we're just making a lot of really grand assumptions, and it's sort of, and I imagine a lot of similar processes happen. A lot of similar complex processes happen with a detonation. And in reality, you should be able to model a detonation, by considering the condensed phase region and all the reactions occurring inside of it. But those conditions are so fast, so crazy, so extreme that there's essentially zero physical understanding of what goes on inside of a condensed phase energetic, a material that's underwent the massive, say, 40 GPa shock that's initiating those basically those chemical reactions. But a propellant, on the other hand, it's a much slower process, and then basically more is known about the condensed phase of a propellant than a explosive, just due to the conditions that it's just much more practical to observe how they burn. Okay. Anyways, so now because of this flame zone, we can't do our nice little energy balance like we did before. And so we need to actually integrate the temperature profile for the gas phase. Whereas for the condensed phase, that was optional. For the gas phase, that's basically mandatory. So let's look at the gas phase, the governing equation for the gas phase. This was derived in one of your homeworks. So it's just the temperature form of the governing equation. And so now I'm just going to basically take this equation, cross out the terms we don't need, and get it to the form that the form that we can actually integrate it. We're going to neglect the Dufour effect. We are neglecting any viscous shear work. We have constant pressure, so this term goes bye-bye. And we're assuming, get rid of this. And again, we are assuming a constant specific heat. So that allows us to make a lot of interesting, a lot of simplifying approximations. So now we just work with the terms. We got the substantial derivative. That's just partial t, partial time, plus u partial t, partial x in 1D. Well, it's steady, so this term goes away, and so we are only left with u partial t, partial x. The divergence of the conduction heat flux, that just becomes dt dx of the thermal conductivity times dt dx. And so basically this term simplifies to this. There should be no surprises there. Now we need to work with the sums. And so we will work with first the interdiffusion heat flux here. And so that term is given by this here. And so we got the sum of rho yi times the diffusion of the diffusion velocity times the gradient of the species enthalpy. And so we can then substitute h. H is just Cp times T. It's the Cp is the same for all the species times a mass-based enthalpy of formation for each species. So we can take the gradient of this. We have the gradient of Cpt plus the gradient of the species enthalpy of formation. Well, the enthalpy of formation is just a constant, and the gradient of a constant is 0. And if Cp is constant, we can yank that out. And then, so this is just equal to Cp times grad T. Okay, so now we're going to substitute basically this in for the gradient of the species enthalpy. And we basically substitute that in and basically pull the terms out that are constant in the sum. And that would be rho Cp and grad T. So we have rho Cp grad T dot with the sum of yi vi. And what's the sum of yi vi? That's 0 by conservation of mass. So basically, this nasty evil term here, because we are assuming constant specific heat, and we are working with the temperature form, that goes away and that's 0. Okay, and so that makes things really nice, really nice and easy. Okay, and then I'll also finish up the sum with the reaction term, and then we'll call it a day. And so I'm just going to expand out the sum of the chemical reaction term here. So this is the sum of the net chemical reaction rate, or the net mass rate of production for species I times times the enthalpy of species I. Again, we're assuming we are in the ideal gas limit, so there's no enthalpy departures or anything like that that we need to worry about. And so we're just going to substitute in our expression for the enthalpy for species I. So that is CPT times a mass-based enthalpy of formation, QI. And then I'm going to split this into 2 different sums. So we have the sum of the net chemical reaction rate for CPI, or for CP times T, times the net chemical reaction rate times the basically enthalpy of formation for each species. Okay, well, CP and T are constant among all the species, so we can yank that out of the sum. And then we are left with the sum of CP times T times the sum of the mass rate of production of over all the species. And again, conservation of mass demands that that term is 0. So this term goes away, and all we are left with is the sum of the mass rates of production among all of the different species. And then only one of our species has a non-zero in our analysis here. Only one of our species has a non-zero enthalpy of formation. And just by the way, we've basically shifted our scales here. And essentially, so basically only the reactants have a non-zero enthalpy of formation. And so this nasty sum here basically just turns into the mass rate of production for the reactants, which are the pyrolysis species, times their enthalpy of formation, or a net heat of reaction, if you will. And because those reactants are being consumed, this here is a negative number. And so I'm going to call this negative omega dot G times basically Q dot G, where you could think of omega dot G is the net gas phase chemical reaction rate on a mass basis, and Q dot G, it should be Q dot G, it should just be QG, and QG would be the net heat of reaction for the gas phase. Okay, and so we will then take these 2 results and then substitute them into our energy equation here. Okay, and that's where we will stop for today. Are there any questions?
Not for me.
Okay. Okay, then have a good day.
Will we be able to get any of the DSD lectures up on YouTube?
Yeah, pretty quick.
Teasing me with those. Keep looking for them. I'm ready.